Welcome back. So we're looking at problem solving in sectors, arcs and circles. Just before I do, I just want to give you a little kind of, let's say, trick or adjustment to way to use these two formulas for arc length. So this is the most beautiful equation we have, because it's kind of based on the definition of the radons, which is length of segment divided by radius. Okay. However, and I just want to corrupt things here and say, what happens if this was in degrees? It's wrong now because it's not in radians. But and I know I need to use pi over 180 degrees, or 180 degrees over pi. And what I just said there about the 180 degrees, I want the degrees to cancel. That's my quick way of remembering that. And I guess it's here, but by cancelling the 2 and the 360, but we shouldn't have to do that. So I kind of want to say, am I writing down r theta, or am I writing down r theta degrees? And if I'm writing down r theta degrees, that's a little nudge to remind me 180 degrees here and pi here. You'll see that very smoothly being used in the rest of the videos. Okay, let's get down to some problem solving. So we have an arc of a circle. The width is 8 and the height is 2 as shown. So there's 2 in here. Find the radius of the circle and find the length. So 2 tasks, radius and the length of the arc. Great. Okay. So there's 2 main big ideas. So I want to introduce the idea of the center of the circle. And I also want to introduce, remind ourselves of Theorem 21. So Theorem 21 is the final theorem on our course. You need to know it, be able to use it. You don't have to prove it, but you should understand the proof. So it literally states, let's have a look down here. So this is an active applet that I wrote, or I edited. I stole one from GeoGebra, and I changed it around and took out a lot of the nonsense. This point I'm moving here is called a dilation point. That makes sense? Because I'm literally dilating the circle from the center. That's a transformation. It changes the size of the original image. The original circle is turning into a new circle. Okay, so I can adjust that around until this segment is 8. And I can furthermore make a kind of a balancing act between the adjustment of the kind of extent of the line segment, how much of the circle it uses up, the proportion of the circle it uses up, and this. So I'm pretty confident that eventually I'll end up with 8 across here and 2 here. And that's what we've been told. So let's argue that is 8 going this way and 2 this way. So the problem is we need to somehow be able to claim that that's a right angle and that this is 4 and 4. And this is where Theorem 21 comes to the rescue. Because it says a perpendicular from the center to a chord. Now that's what you just magic up. You're allowed to do that. That's what's been done here. But what we're saying is, oops, okay, make that a perpendicular. I can't draw into that. It's me. So make this a perpendicular. And if that's perpendicular, then that's 4 and that's 4. Okay, great. Now that's an example of why they're saying, you really got to know Theorem 21. Because if you don't, then you're stuck on this question. Okay. So we know that that's 4, we know that's 4, and we know that's 2. But we're stuck with this variable, this unknown radius. And we need to find it. So I think radius is the first thing to get, and then we'll get L. So we have a length of 4 here, and then because this is a straight through, we can use subtraction. A kind of symbolic expression, like subtraction, symbolic subtraction, to say the radius take away 2, and that would be something you might say to first years. What expression, when you take 2 away from r, what do you get? Well, you get r minus 2. Great. Now we could ask, do we know a triangle with 2 values that are 2 apart? And it might just jump to you. You might just remember, hey, that's just 3 and 5. That fits the thing perfectly. If not, we have to do a bit of algebra. We have to square the legs of the right angle triangle and set them equal to the square of the hypotenuse. Okay, you know well that that's using Pythagoras. You don't have to do a kind of a two-column proof or anything, but it is nice to just say what I've done, because then you'll understand where it came from. I'm going to expand this binomial with d square. You keep the sign and double. It's monic, so just double that, or 4r. And squaring a negative gives us a positive. Yes, r squareds cancel. And get 4r by bringing the 4r across equals 20, and r is 5. But we knew that anyway. I'm going to wipe that out because we've already modeled it that way. So now I want to find out what the length is. And this is where I'm going to apply my kind of thing. Well, I normally talk about the length being equal to r theta, but not if I want it to be in degrees. Now I didn't have to go via degrees. What am I doing now? Well, yeah, first I need to find out that angle. Okay, so if I want to find out that angle, I need to use trigonometry. And because I know all three sides, I can use sine, cos, or tan. Now, often I would say to people, whatever you calculated, don't use it in case it's wrong. But in this case, we've calculated this and this, so there's no better choice just in case kind of thing. So and for that reason, look, sine is probably the first equation that comes to mind. It's better to use sine and cos because they'll highlight mistakes, compared to tan will never tell you made a mistake. So we'll say first that the sine of angle A in here is equal to 4 over 5. Look, that's equal to 0.8, which is handy. And then A is equal to so we have to solve that, so we have to use the inverse sine. And just show you this again, remind you of how we can do this, is that it's a great way to space this out, is to leave space here. And it's the inverse of sining is inverse sining, of course it is. So as you bring the sine across, it becomes inverse sine. You put that in your calculator, and you get A equals 53.13 degrees. Okay, but that's not the central angle, that's half the central angle, so you double it, and you get 106.26 degrees. Okay, I could have done this in radians, and then you could have, sorry for mentioning a radioactive gas, I don't know why I did that, radians. Okay, so what I did, and then I would just simply use L equals of r theta. Okay, that's possibly better. But then you have to be really careful about changing your calculator over and back. And I basically say to you, if you're not doing the calculus section of the course, try to leave your calculator in degrees. Okay. So like I said, now I'm going to calculate the length. And remember, the length should normally look like r, and I'll write it out, the equation, theta, but ours is in degrees, and we have to fix that. So we'll go pi over 180 degrees. That's using the formula for the length of a segment from page 9 when the angle is in degrees. So I have r 106.26 degrees times pi over 180 degrees is L, and r is 5. So you just plug it into your calculator, okay, and it turns out to be 9.27 centimeters. What do I do now? What should I do? I should check, does that make sense? Is that a totally stupid answer compared for the scale and the appearance? So I know that this is 8, and this is quite a big angle, so it makes sense. The bigger angle this is, and it's 100 degrees, it's a good angle. It's gone into being obtuse, so it makes sense that this is quite nice, but a bit bigger. Not a whole lot bigger, so it does make sense. It makes loads of sense. It's what we expect. Okay, so we move on to the second part of the question. The cross section of a piece of corrugated iron is basically loads of repeating, erect, upright, and then inverted, and then erect, and so on. Now it's not a sine equation. And we know that because it told us these are made out of circular arcs. But we know that we know that there's a ratio between the curved section and the straight line, and we know the relationship is 9. So basically, I won't go back up on that. I know you could be getting a bit seasick from the way I move this thing around. But basically, I know we got 8 here, and we got 9.27 here. So this is a kind of a dilation again. Let's use that word again. This is a kind of a scale factor. Okay, that 16 is going to become longer as we stretch it out. Now there is a kind of they've made a few assumptions without mentioning them. We're assuming it's not a ductile material, that when you squash it, that it doesn't end up flattening out and stretching a bit longer, but that's okay. So basically we're just going to take that 16 and we're going to make it a little bit bigger by a factor of this. This is a scale factor. That's lovely. We know all about scale factors in K. Okay, remember that from dilation. So it's a type of dilation, if you like. But it's in 1D, so it's kind of hard to picture. 1D can be bended 1D. Okay, so that's great. We just fill that into the calculator and look, and that's a very basic calculation. And that turns out to be from 1.6, it was 1.6, not 16, and that then turns out to be this value here, 1.854 meters. So that was 1.6 meters and 1.854 meters. Okay. Thank you for your time. Hope that made it clear.